we now start the discussions on the last module, module 3 of chapter 8. So, we are going to establish the versions of fundamental theorem of integral calculus for Lebesgue integration in this module. We are going to see that we can get much improved result than the versions that are available for Riemann integration. So, let us see what we get in our first slide. We start with a result which we will need to prove the fundamental theorem of integral calculus for Lebesgue integration. If f is a non-decreasing function on closed interval a b, then the derivative f dash is Lebesgue integrable, and the derivative has this property that integral a to b f dash d mu is less or equal to f b minus f a. We start the proof. Since f is non-decreasing on closed interval a b, we already know from the last chapter that f is differentiable almost everywhere in closed interval a b. So, in other words, limit h tends to 0 f x plus h minus f x by h exists finitely almost everywhere in closed interval a b. Now, let us define the function f on closed a b plus 1, that is, we extend the function on the right hand side of b also by setting f x equal to f b for all x belonging to open b plus 1 closed, that is, on the extended part we take the function as constant. For each positive integer k, let us define g k x as f x plus 1 by k minus f x divided by 1 over k. Observe that since f is measurable, so each function g k is measurable on closed interval a b, and from the definition of derivative, it easily follows that g k converges to f dash almost everywhere on closed interval a b, because f dash exists almost everywhere. As is the practice, let us set f dash equal to 0 at those exceptional points where it is not defined, and then we see that f dash being the limit of a sequence of measurable functions is also measurable. Evidently, since f is non-decreasing, so f dash is greater or equal to 0 at all points where it exists, as also every function g k, because g k is defined as f x plus 1 by k minus f x by 1 by k, where the numerator is greater or equal to 0. Now, using Fato's lemma, we get integral over a to b f dash d mu is equal to integral over a to b limit k g k d mu. This is less or equal to lim inf k integral a to b g k d mu. Now, if we consider each function g k, then see that each function g k is actually Riemann integrable on closed interval a b, because it has at most countable number of discontinuities. Consequently, integral over a to b g k d mu, this is equal to integral over a to b k into f x plus 1 by k minus f x dx. We can write it as k into integral over b to b plus 1 by k f dx minus a to a plus 1 by k f dx. This is less or equal to f b minus integral a to a plus 1 by k f a dx, and the right hand side is equal to f b minus f a by k. This is true for every k belonging to capital N. Hence, from above we immediately obtain integral a to b f dash d mu. This is less or equal to lim inf over k integral a to b g k d mu, and this is less or equal to f b minus f a, and we get the desired result. Now, we are ready to present the first version of fundamental theorem of integral calculus for Lebesgue integration. If f is bounded and measurable on closed interval a b and capital F of x is defined as a to x f d mu, then capital F is differentiable almost everywhere in closed interval a b, and capital F dash x is equal to f x almost everywhere on closed interval a b. We start the proof. First, see that we have already seen that the function capital F so defined is absolutely continuous, and so is a function of bounded variation on closed interval a b, and consequently capital F can be expressed as the difference of two non-decreasing functions, and so capital F dash x exists almost everywhere in closed interval a b. Now, since by our assumption the function f is bounded, let us suppose that mod f is less or equal to capital K, where capital K is a positive real number. Now, for each positive integer n, let us set g n x equal to capital F x plus h minus capital F of x by h, where we take h as 1 over n. Now, see that for any x belonging to closed interval a b, if we consider mod f n x, so this is equal to mod x to x plus h f x dx into 1 by h, and this is again less or equal to 1 by h x to x plus h mod f dx, and this is finally less or equal to capital K. So, we get that for every positive integer n, mod f n x is less or equal to capital K for all x belonging to closed interval a b, and this shows that the sequence of functions f n is uniformly bounded by capital K. Since from the definition of derivative, f n converges to f dash almost everywhere. So, we can apply bounded convergence theorem to the sequence at any point C belonging to closed interval a b. So, applying the bounded convergence theorem, we have a to c f dash d mu is equal to limit n tends to infinity integral a to c f n x dx, but this is equal to limit h tends to 0 1 by h a to c f x plus h minus f x, and this is equal to limit h tends to 0 1 by h a plus h to c plus h f x dx minus a to c f x dx, and this is equal to limit h tends to 0 1 by h c to c plus h f x dx minus a to a plus h f x dx. See that we can apply change of variables in the above integrals, because the function capital F is continuous on closed interval a b, and so is Riemann integrable. Now, the continuity of the function capital F at the point C implies that given epsilon greater than 0, there is a delta greater than 0, such that whenever mod y minus c is less than delta, we have mod f y minus f c less than epsilon. So, choosing 0 less than h less than delta, we get mod 1 by h integral c to c plus h capital F x dx minus capital F of c. This is less or equal to 1 by h c to c plus h mod capital F x minus capital F c dx. We already know from above that mod f x minus f c is less than epsilon. So, this is less than 1 by h c to c plus h epsilon dx, and this is equal to epsilon. And so, this shows that limit h tends to 0 1 by h c to c plus h capital F x dx, this is equal to capital F of c, and this is true for all c belonging to closed interval a b. And consequently, we have integral a to c f dash d mu, which is equal to capital F c minus capital F a. This is again equal to a to c f x dx by our construction of the function. So, we have integral a to c capital F dash x minus f x d mu equal to 0 for all c belonging to closed interval a b. Recall that we have proved that if for a function f Lebesgue integrable on closed interval a b, a to c f x dx is equal to 0 for all c belonging to closed interval a b, then this implies that f is equal to 0 almost everywhere. So, we have capital F dash x equal to f x almost everywhere on closed interval a b. Finally, we present the other version, a better version for the fundamental theorem of integral calculus for Lebesgue integration. We prove that if f is a Lebesgue integrable on closed interval a b and if capital F x equal to a to x f d mu for all x belonging to closed interval a b, then capital F dash exists and is equal to f almost everywhere in closed interval a b. Now, by the same arguments presented in the last theorem, capital F is differentiable almost everywhere in closed interval a b. So, we need to prove only the equality that capital F dash equal to small f almost everywhere in closed interval a b. Now, since we know that any function f can be written as f plus minus f minus, that is difference of two non-negative functions. So, first assume that f is greater or equal to 0 on closed interval a b. Of course, capital F is non-decreasing and capital F dash is greater or equal to 0 in closed interval a b, because recall that where the derivative does not exist, by our convention we take the value of capital F dash as 0 at those points. So, let us define the function f n as f n x equal to f x if f x is less or equal to n and equal to n if f x is greater than n. We have done this before also several times for each positive integer n, and we know that f n is a monotonically non-decreasing sequence of measurable functions converging pointwise to f, and of course, f minus f n of x is greater or equal to 0 at all points. And so, if we consider the function capital G n x as a to x f minus f n d mu, this is also a non-decreasing function of x for each positive integer n. This must be then differentiable almost everywhere in closed interval a b, and its derivative will be non-negative where it exists. We know this from the last chapter where we had proved that any non-decreasing function is differentiable almost everywhere. Now, applying the first version of fundamental theorem to f n, since f n is a bounded measurable function, we get d dx integral a to x f n d mu equal to f n almost everywhere in closed interval a b. And so, capital F dash x is equal to d dx integral a to x f d mu. We can write it as d dx integral a to x f minus f n plus f n d mu, writing the integral as sum of two integrals. This is d dx integral a to x f minus f n d mu plus d dx integral a to x f n d mu. So, this is equal to d dx capital G n plus d dx integral a to x f n d mu. The first value is always greater or equal to 0. So, this is greater or equal to f n x almost everywhere from the above equality, and this is true for any positive integer n. And so, taking limit n tends to infinity, we get capital F dash x is greater or equal to f x almost everywhere in closed interval a b. Now, integral a to b capital F dash x dx is greater or equal to a to b f x dx, which is equal to capital F b minus capital F a. Now, applying the first theorem that we proved for non-decreasing functions on capital F, we get integral a to b capital F dash x dx is again less or equal to capital F b minus F a. So, combining the two results, we get integral a to b capital F dash d mu is equal to capital F b minus capital F a, which is equal to a to b f d mu. And so, integral a to b capital F dash minus f d mu is equal to 0. Since this function is non-negative, so we get the desired result that capital F dash should be equal to f almost everywhere in closed interval a b. So, finally, suppose that f is an arbitrary Lebesgue integrable function on closed interval a b, then integral a to c f d mu is equal to integral a to c f plus minus integral a to c f minus for all c belonging to closed interval a b, and then by the first part of the proof we get capital F dash c is equal to f plus c minus f minus c. So, this is equal to again f c for almost all c belonging to closed interval a b, and this proves our assertion. So, to summarize, we have finally proved the fundamental theorem of integral calculus for Lebesgue integration, and we have seen that we have got a far better result than the fundamental theorem of integral calculus for Riemann integration, because in the fundamental theorem of Riemann integration, the first assumption is that the function f should be bounded, but here we do not need such an assumption on the function f. Secondly, we need the assumption that the derivative f dash should be Riemann integrable on closed interval a b. Here also we do not need such an assumption. So, we get a far better result in the sense that we have actually proved that if f is Lebesgue integrable on closed interval a b, and if capital Fx is equal to integral a to x ft dt, then capital F is differentiable almost everywhere and capital F dash is equal to f on closed interval a b almost everywhere. So, the antiderivative exists almost everywhere in this case, though the function is not necessarily assumed to be bounded, neither the derivative is assumed to be integrable. The integrability just follows from the assumption. So, with this we end the module.